This is a chapter again about liquids and solids, so we're going to take a look at liquids first. Definition of a liquid. Liquids have a definite mass, liquids have a definite volume, but they take the shape of their container. Alright, when we're looking at liquids and going from liquids to solids or from liquids to gases, we're going through a phase change. We're going to start with the phase change going from solid to liquid, so that is referred to as the melting point. We need to define the melting point in terms of some specifics that we can also use to define boiling point. So the melting point is phase change between solid and liquid. And we define phase changes in terms of vapor pressures. So the melting point of a solid is when the vapor pressure of that solid equals the vapor pressure of the liquid. Now you may not have thought about solids as having vapor pressures, but they do. And how do you know that? Anytime you can smell something, you are smelling vapor particles. So if you smell a candle, if you smell a piece of fresh cut lumber, if you smell pine needles, what you're smelling are vapor particles that were part of the solid. And so as the vapor pressure of a solid increases, there are going to be more of those particles in the air. Vapor pressure of the liquid is simply the pressure a vapor exerts on the liquid it came from when it's in a closed container. When we're looking at phase change from solid to liquid, melting, generally we refer to going from solid to liquid. Freezing would be going from liquid to solid. The other thing we're going to talk about is normal melting point. And the normal melting point is defined as the temperature of the solid when it's melting at standard pressure. Still dealing with liquids, we're looking at boiling point. That's the next phase change. So, boiling point, we're looking at a phase change going from liquid to gas. So when something's going from a liquid to a gas, we have to disrupt all of the intermolecular forces because only the single molecules can get into the gas phase. They tend not to go as clumps of molecules. So we need to disrupt 100% of those IMF, or intermolecular forces. Definition of boiling point is when the vapor pressure of the liquid equals atmospheric pressure. So when a liquid is vaporizing, when it's going from liquid to gas, it doesn't have to be boiling because liquids evaporate. And they will evaporate to make the pressure of the liquid over the liquid surface equal to the atmospheric pressure. That's why when it's very humid out, the atmospheric pressure is high. There are a lot of particles of gas in there. Things don't evaporate as quickly. We have normal melting point. We also have normal boiling point. And the definition of the normal boiling point, the temperature at which the liquid boils at standard pressure. So both our definitions tie back to something changing phase at standard pressure. Okay, another phase change going from liquid to solid is evaporation. And evaporation can occur at a variety of temperatures, but it only occurs at the surface. Differentiating between evaporation and boiling, two ways. Evaporation occurs at a variety of temperatures, boiling occurs at a single temperature. Evaporation only occurs at the surface, and boiling occurs throughout the liquid. When we're dealing with liquids, we are also looking at forces acting on the surface of the liquid. And the first surface force we're going to look at is surface tension. Surface tension is due to the unbalanced forces on the surface molecules, generally in polar molecules. If we look at the diagram, we have a liquid that has attractive forces, so these are probably polar molecules. Those surface molecules are being pulled sideways, and they are also being pulled down. So one way to think about those surface molecules would be to think about them as you would the surface of a trampoline, or if you remember in elementary school when you played with the big parachutes, pulled them tightly, you could bounce a teddy bear or a ball on it. And the reason you could do that is because there was a lot of tension sideways and sometimes down. The molecules that are down in the interior of the liquid are being pulled in all directions, and so they have balanced attractive forces. As the intermolecular forces increase, so as they go from London dispersion to dipole-dipole to hydrogen bonding, surface tension is going to increase as well. Water has a very high surface tension, which is why things can float fairly easily, which is why little critters like water beetles can scoot along the surface of the water. Surface tension is also why water forms beads, or why raindrops are round. If you have a substance and you allow it to just be freely suspended, the shape it will take on is that which gives us the smallest surface area. That's a sphere. Raindrops are relatively spherical. They look kind of teardrop because gravity's pulling them down, and so the tail end of them is kind of getting left behind. But on surfaces that are nice and polished, where water molecules are not attracted, you're going to get bubbles poles like are shown here because the surface molecules attract to each other and the interior molecules attract to everything, and that pulls it to as close to a sphere as it can. It's just sitting on a surface. Two other surface forces or two other attractive forces are adhesion and cohesion. Adhesion is the attraction of a liquid for the container molecules, and if there are similar types of molecules, liquid and the container, they'll attract to each other. Cohesion is the attraction of liquid molecules for each other due to intermolecular forces being different in the container. For example, look at the diagram on the left. We have water, which is a polar substance, and in this case we have a container that is made of something that is also somewhat polar. In this case it's probably glass. Silicon dioxide is the primary substance in glass, and it is a relatively polar substance. So there are going to be attractive forces between the water molecules and the glass molecules. And we see that here because the water molecules and the glass molecules want to maximize their contact between each other, and so the water molecules are going to try and crawl along the surface of the glass as much as possible. What that does is that gives us a meniscus that is concave in nature. So when our intermolecular forces are similar between the liquid and the container, I'm going to have a concave meniscus because the liquid is going to want to maximize the contact it has with the container molecules. There are attractive forces going on there. So if we look at the diagram on the right, this tube has a concave meniscus. So it is this tube. This tube on the right has a concave meniscus, as does this tube on the left. And the others are a different kind. If we take a look at the other surfaces on our right-hand diagram, focus on this one right here. What we have here is a convex meniscus. And in this case, we have cohesive forces that are fairly strong because we have intermolecular forces in one substance different from intermolecular forces of the other substance. So what this may be is if all the liquid in this container is water, then our blue surfaces here are something that is nonpolar. Polar substances do not interact with nonpolar substances. So the attractive forces of the liquid are going to be like that car surface raindrop up at the top. The water molecules are going to try and pull towards each other, and they're not going to try and make contact with the container walls, and so I end up with a convex meniscus. I also have that in this container here, this tube here, and this tube here. Those are convex. The left side here is also convex. Now, why are some of these liquids columns taller? Why are some of them shorter? We take a look. There's two things going on. Adhesion and cohesion work together. So I tend to have taller columns where I have adhesive forces. The liquid is essentially walking itself up the tube, but it's also fighting gravity. Gravity forces are going to try and pull those water molecules down. They want to maximize their contact with the container walls, so they're going to creep up. If it has to pull up less mass, so in the tube right here, it's very skinny. So the mass of water involved is fairly small. So the water molecules can continue to creep up the sides of the glass because they don't have to pull much mass of water along behind them. So the adhesive forces are contacting and attracting to the glass. The cohesive forces of water are pulling all the central water molecules along behind them. They can get pretty high. This is a wider container, and so it probably turns out that the volume of water here in this container and the volume of water here in this container are pretty close to the same above the average surface of the water. It's just that the diameter of the tube is bigger in this container, and therefore the water can't get as high. This tube